meal timing, gut microbiome rhythms, and metabolic health. The temporal dimension of gut microbiome function represents one of the more fascinating discoveries in recent microbiome research, revealing that bacterial communities exhibit their own circadian oscillations synchronized with host feeding patterns. This temporal organization extends beyond simple microbial abundance to encompass functional metabolic activities, creating a dynamic system where timing and composition interact to influence host physiology. The implications for understanding how meal timing affects metabolism may run deeper than previously recognized, operating through microbial intermediaries. Controlled feeding studies with serial stool sampling across 24-hour periods demonstrate that microbial community composition and metabolic output exhibit diurnal rhythms under typical eating patterns. Short-chain fatty acid production, bile acid transformation, and vitamin synthesis all show temporal variation tied to feeding schedules. When researchers shift eating windows through time-restricted eating interventions, these microbial rhythms reorganize accordingly. The microbiome appears to anticipate and respond to feeding times, adjusting its metabolic machinery to match nutrient availability. This plasticity suggests that changing meal timing could theoretically optimize host microbe metabolic synchrony. However, translating these temporal microbial shifts into meaningful host metabolic outcomes proves more challenging than the mechanistic possibility suggests. While time-restricted eating alters microbiome rhythms, the downstream effects on glucose metabolism, insulin sensitivity, and other health markers appear modest in isocaloric contexts. This disconnect between microbial reorganization and host physiology likely reflects the multifactorial nature of metabolic regulation. Microbiome metabolites contribute to host metabolism, but they operate within a complex system where multiple regulatory axes exert influence. Temporal microbial shifts may produce subtle metabolic effects insufficient to override other dominant factors like total caloric intake or macronutrient composition. The specific metabolites merit closer examination. Short-chain fatty acids, particularly butyrate, exhibit temporal production patterns influenced by feeding schedules. These metabolites affect intestinal barrier function, immune signaling, and potentially glucose regulation through complex mechanisms. Similarly, bile acid metabolism shows circadian variation, with secondary bile acid production shifting in response to altered meal timing. The host receives these temporally structured metabolic signals, which may influence everything from hepatic glucose production to incretin secretion. Yet individual variation in microbiome composition means that identical eating schedules produce different metabolic outputs across people, complicating predictive efforts. This emerging understanding suggests that meal timing's metabolic effects may partially operate through microbiome-mediated pathways, but these pathways interact with direct host circadian mechanisms and caloric balance in ways not yet fully characterized. For individuals interested in microbiome health, maintaining consistent eating schedules may help optimize microbial rhythms, though whether this translates to measurable health benefits remains uncertain. The research highlights the sophisticated temporal coordination between host and microbiome, revealing yet another layer of complexity in nutritional chronobiology. As sequencing technologies improve and larger cohorts undergo longitudinal sampling, clearer pictures may emerge of which individuals might benefit most from timing-based microbiome interventions and which microbial signatures predict successful responses to time-restricted eating.